All right, so we don't know. Your brain's gonna hurt. We're not sure about this topic. I'm gonna present the latest ideas, but they could be completely wrong. We're just gonna go with it. Today, taking a look at dark matter and dark energy. If you guys could write down the questions of the day: what is dark matter and dark energy, and how do we even know that they exist? Evidence gathered from WMAP, which is the satellite that took a picture of the cosmic microwave background radiation, tells us that matter in the universe has 3 different types. First one is cold dark matter, which are basically huge blobs of dark matter. Then you have hot dark matter, which are very small little particles that are moving extraordinarily fast of dark matter. And then you have baryonic matter. Baryonic matter, remember, are protons and neutrons. That's what we're made out of. That's what the sun's made out of. That's what Earth is made out of. That's what every single thing that you can see in the entire universe is made out of baryonic matter. So just regular stuff, that's known as baryonic matter. If you guys remember the Tully-Fisher relation, where we look at the rotation of galaxies to tell how fast they're going, therefore how bright they are, therefore how far away they are, when we take a look at those galaxies that are spinning, we can calculate how much stuff should be there in order to hold those stars in place. Over 90% of the mass that has to be there, according to how strong we've measured gravity, 90% of the matter is invisible. So to have a galaxy spin at the speed that they are all spinning, you have to have way more gravity than what you would get from just visible material. So 90% of the matter in a galaxy is dark matter. Do we know what it is? No. But we know that there has to be something there that causes gravity that we cannot see, because galaxies are just spinning too fast. When we take a look at all of the matter in the universe, this is the breakdown. About 4% is that really super fast, almost the speed of light, very small particles, what's known as hot dark matter. About 15% is baryonic matter. So if you added up every star, every galaxy, every planet, every alien in the universe, that would come up to about 15% of everything that exists. And then about 80% is cold dark matter. We don't know what it is, but we know that there are big blobs of it. It's not really moving. It's basically surrounding galaxies. About 80% of the matter that exists in our universe is dark matter, and we have no clue what it is. What do we know about dark matter? A little bit. It's some sort of matter that does not emit or reflect any sort of light, but it does have a gravitational influence. So, as I mentioned, we can see it when galaxies are spinning. Stars should be flying away, but something is keeping them gravitationally bound. We can see it when galaxies in a galaxy cluster are rotating around a center of mass in that galaxy cluster. They should be flying apart, but those galaxies are being held together by something. We can see it in the temperature of intracluster gas. So there's interplanetary, there's interstellar, there's intergalactic, and then there's intergalactic cluster. And the gases that are in between galaxy clusters have a temperature, and it's higher than it should be because something is giving it gravitational energy. We can also see distant galaxies that are gravitationally lensed, meaning the light is bent, but there's nothing there to do the bending. There's nothing there to gravitationally lens them. People might think, well, maybe it's a black hole. A black hole is not nearly big enough. Even a supermassive black hole is not nearly big enough to gravitationally lens an entire galaxy or an entire galaxy cluster. Has to be something with a ton more mass than a black hole. But there's nothing there that we see doing that. Dark matter. Of course, astronomers are going to have fun with naming these things. So what do they call different types of dark matter? There's machos and there's WIMPs. Machos are going to be big pieces of dark matter, like the size of a big planet or a little star. That's the cold dark matter. The other one is a WIMP, a weakly interacting massive particle. And these are like subatomic particles with very tiny little masses. And you might think, why do you name something with a very tiny mass a massive particle? That doesn't mean that it's very big massive. It means that it has a mass. They're so tiny, like a photon doesn't have any mass. But these technically have a very small little mass. So they're known as massive particles because they're a little tiny itsy bitsy particle that does in fact have a mass. When we put a model together of what a galaxy should spin like based on what we can see, we get this over here. If you only take into consideration the stuff that we can see, the stars and the planets, the amount of matter that's regular baryonic matter, galaxies should be spinning much, much more slowly. Because if they spun any faster than this, the stars would just fly apart. However, what we actually see is stars spinning much quicker than they should. And at this speed, what we actually observe, these galaxies should have flown apart billions of years ago. But they haven't, which means there's something there holding that galaxy together. We don't know what it is. We can't see it. We can't detect it other than the fact that it has gravity. We also use the redshift of galaxies within a galaxy cluster to figure out which direction that galaxy cluster is moving. And then we look at the next galaxy cluster, and we can tell that galaxy clusters are actually moving around a common center of gravity. This is a huge timescale that takes many billions of years to complete, but we can still measure it because of redshifted light. Well, those big giant galaxy clusters should not be moving around a common center of gravity. They're too distant. Gravity should be too weak if you only take into consideration stuff that we can see. But if you add in a bunch of extra dark matter, now there's enough gravity to cause these galaxy clusters to start to orbit some common center of mass. So galaxy clusters are behaving in a way that they shouldn't be behaving if dark matter didn't exist. The only way that we can explain why these galaxy clusters are doing what they're doing is dark matter, even though we don't know what it is. If you look closely, this is a version of the Hubble Deep Field. These are not individual stars. Well, some of them are stars. You can see the plus signs. But this is a picture with a whole bunch of galaxies in it. And you can see quite clearly that there are gravitationally lensed galaxies. These lines right here. The problem is that there is no object there doing that gravitational lensing. As I mentioned, black holes are not big enough. So if there was another galaxy there, that might be big enough to gravitationally lens farther back galaxies. But we don't see a galaxy doing the gravitational lensing. So there has to be some material there, something with a bunch of gravity that can bend space-time and cause the light from distant galaxies to bend that we can't see. We can't see it, we can't detect it, we can't measure it, but we know it's there because we can see its effect through gravity. We call it dark matter. By taking a look at those distant gravitationally lensed galaxies, we've actually been able to plot, using a computer, how much dark matter is in between us and them, as well as where that dark matter is most likely located. And this is a halo of dark matter around our Milky Way. And you can see that our Milky Way, while it's huge and there's a lot of stuff in it, is actually very tiny compared to this giant clump of matter, a full solid sphere of dark matter, which makes our galaxy look tiny in comparison. If you look at the overall mass of our galaxy, the vast majority of it is dark matter. The vast, vast majority of it is stuff that we can't see. The stuff that we can see makes up a very tiny little bit of the overall mass. What is this stuff out here? Well, they've made it this bluish purple. I'm colorblind, so I don't know what color that is. The problem is that in real life, we can't see it. It's not like a big cloud out there. It's made that color so that you can see it in this demonstration, but in real life, it's completely invisible. We can't detect it. We don't know what it is. We know it's there, though, because we can see its effects through gravity.
Dark matter. What's the matter with dark matter? Fritz Zwicky was a Swiss astronomer who could probably get you 81 points on a triple word score in Scrabble. In the 1930s, he noticed that galaxies within clusters were zooming around far quicker than their mass would logically dictate. So he figured that there must be some extra mass in there, some sort of dark, invisible matter slurping around the universe. He imaginatively called this dark matter, dark matter. But the problem is trying to prove it, because unlike other dark things, you can see right through this stuff, and this gave Zwicky another idea. According to Einstein's theory of general relativity, the more mass something has, the more it magnifies and distorts objects that you can see through it. So by studying the distortion of distant galaxies, we can calculate that there must be some extra mass between us and them. But because we can't see it, touch it, or weigh it, it's not surprising that we can't figure out exactly what it is. And that's what the matter with dark matter is. It makes up most of the mass in the universe, but when it comes to knowing the details, we're still in the dark.
The universe has a bunch of stuff in it. It's got the planets, the stars, the galaxies, and gas and dust, all the regular space stuff you hear about. But a lot of what makes up the universe cannot be seen with a telescope because it doesn't emit or absorb light. It's called dark matter, and surprise, surprise, it's very mysterious. Since dark matter can't be detected, you might wonder, why do we even think that it exists? Well, we can infer its existence from things that we can detect, like light and other forms of radiation, plus all the things that they bounce off of that lets us see them. The first clues to dark matter's existence came in the 1930s, when astronomers realized that they could weigh a faraway galaxy by clocking the rate at which all of the massive objects inside it moved in relation to each other. This gravitational action could tell you how much mass there was in the galaxy. The galaxies appeared to be weighing a lot more than the stuff inside of them would account for. There simply weren't enough stars and other stuff to make the galaxies act the way that they were acting. There had to be something massive, yet undetectable inside of them that explained how they moved and also what was keeping them hanging together. It took decades of brilliant people and amazing instruments like the Hubble Space Telescope to rethink the whole enchilada, but today, physicists figure that dark matter accounts for about 23% of the known universe. So now comes the part where we tell you what dark matter is, what it's made of, and tell you all about it. Unfortunately, nobody knows. We're pretty sure that it's not just regular everyday matter, also called baryonic matter, like protons and neutrons. The most commonly held view is that it's made up of exotic subatomic particles that were created a fraction of a fraction of a fraction of a second after the Big Bang, and it might be all around us. We could be swimming in dark matter, and we would have no idea because its particles don't interact with ordinary matter, so we can't detect it. Now, what's got astrophysicists all hot and bothered these days is the possibility that the newly discovered Higgs boson might hold the key to dark matter. The Higgs, remember, is a particle that's predicted by the Standard Model of Particle Physics, the theory that helps us understand the behavior of matter in the universe. Verifying the existence of the Higgs is a huge deal because it's an indicator of a larger phenomenon known as the Higgs field, an invisible field that basically gives particles mass when they interact with it. So, even though dark matter and ordinary matter probably can't interact with each other, some scientists think that the Higgs might be able to kind of translate for us. Since it gives mass to ordinary particles in the universe, it probably would also be giving mass to whatever makes up dark matter, seeing as dark matter is also massive. So unlocking the secrets of the Higgs could end up making dark matter a lot less mysterious. In the meantime, scientists are doing their darndest to actually detect dark matter. Most of these experiments are happening deep underground because if we're surrounded by this stuff, which we probably are, then it's likely passing right through our planet all the time.
So what's my final answer? What is dark matter? No clue. We don't know. We do not know. It's never been observed. It's never been detected in a laboratory. We just know that there's something there because we see its effects through gravity. And as gravity affects things that we can see, things like galaxies and galaxy clusters, there's something there, we don't know what it is. I want you to remember this. Energy equals mass. Mass equals energy. When you talk about how much stuff is in the universe, a lot of people want it to be just, planets, stars, galaxies, maybe even throw dark matter in there. You're counting all of the mass. You're counting all of the matter. You also have to count all of the energy. Energy is also in the universe. And mass and energy are equivalent. You can go back and forth as long as the temperature is hot enough. So you have to, when you talk about how much stuff is in the universe, count up all the mass and all the energy. And when you count up all of the stuff that's in the universe, about 22% is dark matter, about 4% is baryonic matter, so stuff that's made out of atoms, and about 75% is dark energy. So most of what's in our universe, 3/4 of it, is dark energy. Why can we put matter and energy on the same pie chart? Because mass equals energy, energy equals mass. They're the same thing. They can go on the same pie chart. And because we can't detect dark matter or dark energy directly, these are pretty accurate estimations, but they are estimations. So depending on where you look, you'll get 74% dark energy. This one says 73%. They're all roughly about the same, but you might see 1 or 2% differences because we can't detect any of this stuff. What is dark energy? First, it is something that is horribly named because we don't know if it's energy. It might be matter. It might be mass. We don't know. What is it? It's stuff that we've never been able to detect. It's stuff that we can't see. It might actually just be a property of space itself. We don't know. But it is whatever's causing the expansion of the universe to speed up. And if we take a look at how fast the universe is speeding up, as well as how big it is, we can calculate how much energy there has to be that's causing that to happen. That's how we know how much dark energy there is. We don't know what it is. We don't know where it comes from. We don't know how to measure it directly. We don't know if it's going to go away in the future. We don't know anything about it. We know that something is there, a lot of something, and is causing the expansion of the universe to speed up. So if we take a look at distant galaxies, we know that they're moving away. And we know that they're moving away faster today than they were last week. And they're moving faster last week than they were the week before. We know that it is speeding up, how fast these galaxies are moving away from us. The universe, the expansion is speeding up. Dark energy is the name for the cause of that. We don't know what it is, but it's 74% of the universe's total energy budget. So if you took all the mass and converted it back into energy, which is what like a nuclear bomb would do, think of converting every single atom in the universe back into energy. That still would only be 4% of the total amount. 74% is this dark energy stuff. Maybe it's always been there. Maybe. But when the universe was younger, gravity was stronger. Remember that gravity is stronger when you're closer to something. So if the universe is smaller, everything's closer together, gravity would be pulling on everything with more force. As the universe expanded, maybe it got to a point where everything was so spread out that gravity was weak enough where this dark energy, which had always been there, was all of a sudden stronger than gravity. And at that exact moment, when everything was spread out so that gravity got weaker and weaker, as soon as dark energy was stronger, the expansion started speeding up. We don't know for sure, but that's an idea. We've mentioned too that this is Einstein's cosmological constant. If the universe was static, everything was just staying still, gravity would pull everything together. But we don't see that. So there has to be something there going against gravity. Dark energy, there it is. That was easy. We still don't know what it is. We know it's there because the expansion of the universe is speeding up, but we don't know what it is or how it works. We don't really know what kind of energy it is either. I like to think of it as anti-gravity energy because that's kind of what it's doing. It's counteracting gravity, but we don't know.
Dark energy. Why is the universe expanding? Albert Einstein was absolutely certain the universe was stable, but he couldn't work out why his snazzy new relativity equations suggested that it was contracting. So Einstein figured space must have an inbuilt tendency to fling itself apart, which would balance out the pull from gravity. This flinging outness got called the cosmological constant and meant the universe could be kept static, which was great, until it was proved by Edwin Hubble that the universe is in fact expanding, and that cosmological constant became what Einstein described as the biggest blunder of my career. Then, in 1998, scientists discovered that the universe was not only expanding, but that expansion was actually getting faster. So either space does have a tendency to fling itself apart, or there must be some other hidden weird stuff in the universe causing it, referred to as dark energy. Astronomers are looking for it right now by measuring tiny kinks in space. And in its simplest form, this dark energy is pretty much a cosmological constant. So Einstein was right all along, apart from the time he said he'd blundered. The big thicko.
As you are probably aware, our universe is huge. But what you might not be aware of is that it's getting huger all the time. And for that, we have dark energy, the most mysterious force ever, to blame/thank. So the universe is expanding. not only that, but the farther away you go in any direction, the faster everything's flying apart from everything else. Now, we've known since 1929 that the universe was expanding. That's when astronomer Edwin Hubble, you recognize that name, noticed that light from other galaxies was shifted toward the red end of the spectrum, indicating that they were flying away from us. But it wasn't until 1998 that astronomers observing distant supernova discovered that the universe was actually expanding at an ever-increasing rate the farther away we look. Now, this is really counterintuitive given everything we know about the Big Bang and our old friend gravity. As you've no doubt heard, the Big Bang theory suggests that the universe came from a single, unfathomably dense point, and the crazy amount of energy generated by the Big Bang caused everything, space, time, matter, everything, to come into being and radiate out from that point. And for about 3.5 billion years after the Big Bang, things went along about as you'd expect. The expansion of the universe gradually slowed as gravity tried to pull all the matter in the universe back together. But then, something weird happened. Another force began to overpower the pull of gravity between all the matter and made the expansion of the universe accelerate. Spoiler alert, that's what we call dark energy, thought to make up more than 70% of the energy in the whole universe. But as bizarre as this is, as physics go, it isn't totally out of left field, because Albert Einstein actually predicted it in 1917 when he was first trying to apply his new theory of general relativity to the structure of space and time. Einstein found that his equations didn't work for a static universe, so he threw in a hypothetical repulsive force that he called the cosmological constant in order to fix his math problem. This constant was basically a certain density of energy that was theorized to permeate the universe. The funny thing is, once Edwin Hubble discovered that the universe wasn't static and was in fact expanding, Einstein thought that the cosmological constant was no longer necessary and he scrapped it. But now the concept is back on the table as a way of explaining dark energy. So what is now known as the cosmological constant theory assumes that dark energy is just a fundamental property of space. In keeping with Einstein's thinking, it proposes that empty space is not nothing. It has properties like anything else. One property of empty space is that it can grow. More of it can be made. Another property is that it can possess its own energy. And if dark energy is a property of space, as more space comes into existence, more dark energy would appear. Another theory that some are pushing is called quintessence, named after the fifth element of Greek philosophers. Quintessence suggests that dark energy is a new type of energy that is temporarily filling space, but it might eventually fade away just as it arose. And there are other ideas. Some think that dark energy fills space with virtual particles that only briefly exist as matter and then disappear, while others are ready to entertain that Einstein's theory of gravity is incorrect, which could be a kind of game changer, as you'd imagine. So the bottom line is, whatever dark energy is, and whatever it's doing it like crazy. But everybody wants to know more about dark energy, so hopefully we'll have more information soon.
What I would like you guys to do is compare and contrast dark matter and dark energy. They have some things that are in common, they have some things that are different from one another. Come up with at least 3 things that can go in this section, 3 things that can go in this section, and 3 things that they have in common. Underneath those 3 things, I would like you to make one hypothesis about what it is. I also want you to write down at least one way that we know that dark matter is there, and at least one way that we know that dark energy is there. If you guys could go back and answer the question of the day, I'd appreciate it. And then we look at the next